Thank you for joining the Phoenix LiDAR Systems September 2021 webinar. This is the new edition of our monthly webinar series. The topic of this month is Airborne LiDAR Data Acquisition, focusing on manned aircraft. And our hosts today will be Conrad Quinterno and Ben Adler. So Conrad, why don't you go ahead and take it away? Let's get started.
All right, thanks, Lito. And thanks everyone so much for joining the webinar today. Phoenix LiDAR specializes in compact and flexible mapping systems. Although our core has centered around the payload, we go beyond just the hardware and dedicate ourselves to building turnkey solutions that range from planning and acquisition to post-processing and delivery of data. Here at PLS, we are constantly striving to push the boundary of what's possible. Our intention is always to develop new ways of improving efficiency, data quality, and accessibility of the technology. No matter what your goal is with a remote sensing payload, we're here to help find a solution that works best for you. As Lito mentioned, the focus of today's webinar is going to be planning and execution of manned aerial LiDAR acquisitions. My name is Conrad Quinterno. I'm the post-processing manager, and today I'll be joined by Ben Adler, the CTO and co-founder of Phoenix LiDAR.
Hi all, thank you for joining. I'll wait for my part in the webinar, but thank you guys for your attention.
The specific topics that we're going to cover today are, first we'll start with some general remarks about manned data acquisition and special considerations about these types of missions. Then we'll be discussing planning a flight, and finally move on to acquisition execution with our new software for real-time mission guidance. Let's begin by discussing a really zoomed out overview of manned acquisition. I realize that some of you in attendance are experienced with airborne data acquisition, while some others have UAS experience but may not have ventured into manned flights, and others may just be getting started in the LiDAR world. So in this section, let's take a step back and review some fundamental considerations. In a world where we can collect LiDAR safely from a UAV, why would we even consider other vehicles? It ultimately comes down to a few major advantages that a fixed wing or helicopter can offer to remote sensing efforts. Flight speed and height can both usually be substantially increased, and this creates huge gains in the productivity of a scanner. Larger swath footprints from faster moving vehicles cover way more area over time, meaning simply better efficiency. The flight time or endurance is generally a limiting factor for UAS. Helicopters, on the other hand, can fly for significantly longer in general, so that's another major efficiency gain. Manned vehicles can travel much further than unmanned, so it's possible to cover large project areas and long corridor projects in a single flight and not be bound by visual line of sight or radio equipment limitations. They also generally have much more capacity for carrying heavy payloads, which is really important if you want to be able to fly higher and faster. And finally, site accessibility. There are just some areas that aren't reasonable or legal to acquire from other types of vehicles. So it's fairly easy to make a case for utilizing manned aircraft simply based on these few advantages. But we also need to realize that there's an increased operational cost, and that creates a type of a risk versus reward situation that we need to feel confident about. Acquiring the correct data on your first try is increasingly important when the cost to perform a refly goes up. And because of this, there are some special considerations when planning for data acquisition. These considerations aren't necessarily unique to manned acquisition, but in some cases, they're more significant for this particular application. First of all, there's point density, and this is a standard project spec that frankly needs to be met. Often it only really becomes a serious planning consideration when we're flying at manned vehicle AGLs or speeds. From a UAS, for example, the data is usually or often so dense that we don't even think about point spacing as an obstacle. And that's not the case when you're flying hundreds of meters above the ground. Collecting with improper settings from these survey speeds and heights could easily result in the need to remobilize and redo a project. And that's definitely something that we don't want to happen. Other considerations include range capability. When scanning at longer distances, we must ensure that the pulse energy is great enough to measure its target. So users need to be aware of the settings they're choosing, like pulse repetition rate, and check that they're compatible with the intended measurement distances. Maintaining proper overlap for LiDAR and imagery is another aspect of well-planned data acquisition. As a vehicle travels across areas of significant terrain relief, the footprint and resolution of your acquired data can change dramatically. This can cause two issues. Either number one, you're suddenly too high above the target and not capturing the proper resolution, or number two, you're too near the target and your forward and side overlap are minimized below what you were intending. Usually a terrain following flight path can mitigate this type of obstacle. Finally, when the time of flight for a LiDAR pulse is greater than the time between consecutive pulses, there can be multiple shots in the air simultaneously. This can cause an ambiguity as to which emitted pulse the return belongs to. The ambiguity can be resolved, but with some data sets, you may notice that there's a specific range at which these ambiguities cause either artifacts or dropped pulses. These border zones are luckily predictable, and if possible, it's best to adjust your flight plan so that they do not occur within the planned target ranges. Keeping in mind that there are multiple data quality considerations that are an important aspect of a successfully executed acquisition, it's clear that a well-designed flight plan is a critical piece of the overall mission. So next, let's take a look at the process of creating a flight plan. Current users of Phoenix systems have had access to our UAV flight planner for a few years. Now that flight planner has been expanded to include options that are useful for missions from a variety of vehicles. We're pretty excited to offer this homegrown option, so let's dive into the key functionality. Oops. The PLS flight planner has 3 different mission type modes that are applicable for different scenarios. First, we have the wide area mapping mode. This mode is not new to Flight Planner, but there have been some alterations that are conducive to following discrete lines instead of the waypoint following UAV-oriented output that previously existed. Then there's the corridor mapping mode, which is useful for planning linear areas of interest like utility corridors, for example. And finally, a new type, which is line points mode. This is used for planning complex paths like bore site calibration patterns. These missions can be built using imported KML areas of interest, or they can be built from AOIs that are digitized directly in the flight planner. We've also added the ability to save missions to our server and to have multiple missions, possibly of varying types, even open in a single project. So for example, if you plan a wide area acquisition and also want to perform calibration during the same flight, that's pretty easily achieved. In order to plan appropriately, the flight planner has a variety of sensor types that can be added to a mission and specific sensor models that are available. So you can plan a mission that includes a LiDAR plus a camera or plus multiple cameras at the same time. With the specific sensor models, we can choose which settings to use, and the flight plan output will be estimated based on those settings. This sensor-specific criteria allows accurate planning for key aspects like density, overlap, resolution, etc. The parameters which control how your flight plan will be automatically designed are very visible and they're in your control. Toggling these is quick, and so you can easily fine-tune things to reach your desired outcome. There are some straightforward parameters like, for example, would you like to terrain follow or not? What speed and altitude would you like to use? What's your usable field of view, etc. These are the more foundational settings. There are also some ways to customize for efficiency and quality, like setting flight direction to best suit your AOI, or to create north-south only passes to optimize image quality based on illumination conditions. Once your parameters are set, the flight plan can give both visual and statistical results for your quality control. The visual results are various map layers, including generated flight lines, point density estimates, MTA zone borders, image resolution, and other clues to help you know if the plan is what you need. The statistical output will show you interesting properties of the LiDAR like point spacing and swath widths. You'll get estimates of camera output, and you'll also get properties of the flight itself, such as duration, distance traveled, and line spacing. If adjustments are needed, you just toggle the previously discussed parameters or make changes to the scanner settings and recompute the plan. Really, the purpose of these visual and statistical results is to ensure that you have the right plan for a successful mission. The final step is to output your results. There are outputs that are compatible with a few different flight controllers. The one that we're particularly interested in for manned aerial acquisition is the Spatial Explorer output. This will generate a plan that can be used directly in the new real-time mission guidance functionality of SE. So let's move into that section of the webinar as I hand the mic over to Ben.
Thank you, Conrad. Can you hear me?
Loud and clear.
Cool. Yeah, so now that we know why we would create a flight plan and how to create it, I'd like to show you how to use that in the field. And I thought to introduce mission guidance, which is the new part of Spatial Explorer, a 15-minute demo would be much more helpful than slides. So let me try and share my screen here and demonstrate this. 1 second. So normally in the field, you would connect to Rover, either using Wi-Fi or Ethernet or 4G, whatever it is. for the purposes of this demonstration, I'm just going to use the offline mode, and I will load a trajectory that we acquired last May. Mission guidance really works the same independent of whether the poses are coming in from a trajectory, from disk, or from the rover that you're connected to in real time. So really what you're seeing should be the exact same thing. Now, this flight was flown in an R44, and you can see here we're taking off, gaining some height, then we're moving over to a calibration pattern here. So there's some lines flown here at 2 different altitudes, and then we're moving over to a mapping pattern. And if we zoom out a bit, we can see that this was flown just north of Austin at the Georgetown Municipal Airport. And yeah, I want to focus on the mapping part of this. So first of all, I'll start playing this at right around real-time speeds, and I'll play this. And because I know the navigation system is going to initialize the first couple of minutes, I'll just jump ahead to maybe a more interesting part. But in the end, once you're connected to rover, even if the navigation system is still, say, aligning or initializing, you can already start mission guidance. And of course, in practice in the field, you would be moving this window to the pilot screen, which would be connected to your laptop via HDMI. So the left side would be for the sensor operator and the right side would be for the pilot. You can already see this is us. Here's the current velocity, our current height above ground, a heading, and an estimate of when the flight plan is complete. Of course, right now we don't have a flight plan loaded, so this is kind of useless right now. But if we seek ahead here a little bit, we can already see ourselves moving. And what you see here is what we call the dynamic whisker. So this gives you a good idea of your current curvature, and if you keep flying with this curvature, where you're going to end up in the future. Let me close this here and this. Okay, so the idea, of course, is to fly with a flight plan. So let me load that. This file was created using our Phoenix LiDAR flight planner. So I'll just open that, and really you can just open any KML. All we need to know is, since KML files can have folders, from which folder to import the geometry, and you can select multiple, but really all we want here is the flight lines, and we want to limit this to line strings. So really just paths, not polygons or points, just lines. So I'll just press OK, and immediately we'll have, in this case, 10 flight lines in here, and they show up in the operator view in 3D, and they also show up here for the pilot. Now, in terms of flight plans, you can load multiple flight plans, which will show up here. And each flight plan consists of any number of flight lines. Flight lines can have a status. Here you can see after loading they're all blue, which means that they are incomplete. You can schedule a flight line, in which case it'll turn yellow, so you use the yellow button for that. And then that tells the pilot to please approach this flight line because it's going to be mapped next. When the pilot gets close enough to one of the endpoints of it, it'll switch into recording mode, or active mode, which is red. And when the pilot did a good job and passed that line, it'll turn to green. So the idea is that blue will slowly turn to green over time. Now, before we go there, I want to draw your attention to, let's focus on this part here. I would like to draw your attention to this flight plan because it has a couple cosmetic issues here. You can see the flight line not really being very smooth. So it is terrain following, but something is up there. Now, as you can already see here, Spatial Explorer has a model of ground. And we want to use that to fix up this flight plan. So even though there already is a model of ground, we have some additional flexibility in allowing different height maps to be used for this. So in order to make edits to flight plans, you will need to download a height map. And for that, you can conveniently go to grid.phoenix.com, and you'll be presented with a rather overwhelming amount of height maps. These are both geoids that we use for post-processing, as well as height maps that we use for mission guidance. And usually I would recommend for mission guidance, you should be using the low resolution SRTM version. And if you really need to, maybe because you're flying higher latitudes, then I would recommend you switch to Aster, which has much better coverage. It's maybe not quite as accurate, but is still going to be good enough for mission guidance. Now, I'll stick with SRTM version 3, and I already know I'll be flying in Austin. So right around here, Georgetown, there we go, and whoops, here's the airport. So I'm just going to click this, and then when this is selected, I'll see the right height map down here. I can just download that right away. It'll be like a 70 megabyte TIFF file. Or if you find yourself in the hangar, or worst case, sitting in the helicopter realizing you're missing a height map, I would recommend you download the zip file because it's just much faster. Of course, you can also download multiple if your mission spans multiple height maps here. In the end, those height maps are going to have to go into this folder, so Documents, Phoenix LiDAR Systems, and Height Maps. And I'll really only be needing this one, but yeah, I can add as many as I want to. Once I have that, I can come back to my flight plan here, and I can go and recompute the altitude, and it'll remind me that it'll need height maps in this folder. I'll say OK, and then I'll tell it to reflow those flight lines 3,300 feet above ground. And when I say OK, it'll say, OK, I recomputed 5,000-ish positions, and none of them were not covered by height maps, so that's good. Once I press OK, you can now see the flight lines are much smoother and following ground much better. Of course, you can also just, if this were a UAV mission, you could go and just set this to 400 feet, and it would land down here. Now, if you're happy with the shape of the flight lines, just not their absolute altitude, you could also go in here and just apply an offset. So I just said 400, it was 3,300. So if I add another 2,900 feet on top of it, I should be back to where I started. And then, of course, you can also go back and undo this and recompute them to, recompute them to 3,300 feet, and I would be back up here. So this isn't just helpful when importing flight plans from other programs shows up with issues, and we've seen mismatches from, say, EGM 96 to WGS 84, or even units being incorrect, or just downright heights of 0 being exported. So I would recommend that you have some height maps ready just in case. We also had missions where, for example, cloud cover prevented us from flying at the altitude that we wanted to fly. So it's quite handy to be able to change this before or even in flight. Okay, so to keep this video short, I want to go ahead and go to the beginning of, say, flight line number 1, and I do want to fly this flight line first, but really in terms of the flight plan, flight line 0 is first. Now maybe that's a flight line that I really don't want to fly, and I can rename this, for example, to be named unused, and I can select one or multiple flight lines and just move them around using drag and drop operation. For example, I could move this to the end of the flight plan, so that I would only fly this if we have fuel left. Or sometimes you can have air traffic forcing you to make changes to the flight plan because maybe you can't fly flight line 7 and 8 right now, so you'll just move them to the end of the flight plan, and so on. So that way you can just pick a couple flight lines and move them to any place that you like. It's not going to change their status. Once they're complete, they're complete. Now, if I jump to this point in time, and I'll start playing this back like this, you'll see that mission guidance directs the pilot to the first incomplete flight line, which now is flight line 1. You can also uncheck this here to remove some clutter. And we see the pilot making his way to this, but the flight line isn't scheduled yet. So I'll just manually, it's already selected, so I'll just hit the yellow button, and then you'll see the pilot approaching that, and we see the flight line itself, which is now yellow, as well as a corridor, like a horizontal tolerance around it. And so long as the pilot hits that horizontal tolerance and also hits the vertical tolerance here, the flight line is going to switch to active or recording, so it should turn red. Okay, so now we're on the flight line and the yellow line switched to red, and we know we're recording, and we actually see how the pilot is navigating here, both horizontally and vertically. There's a slim line here at the top that shows you your progress along the current flight line, and there's another slim line that shows you your progress along the flight plan. And once you're on a flight line, this estimated time remaining also makes a bit more sense. Of course, it's just an estimate, but it gives you a rough idea, and pilots really like it for planning their fuel, essentially, if they do need to land and fuel up or not. Now, to keep this short, I'm going to jump towards the end of this flight line, so right here. And I'll jump over here, and now you can see the flight line progress being much further, the flight plan progress also being a little further, and we should see the end of the flight line coming up also in this vertical view. And once that happens, of course, we have no flight line scheduled here, right? They're all incomplete. And then mission guidance is smart enough to just pick the next incomplete flight line, which is flight line 2. And you'll see the view immediately changing. It always takes care that the point of interest, in this case the beginning of the next flight line, is always in view. So no matter where you fly, no matter which way you turn, you'll always see that point. And again, we can see how you can use the dynamic whisker to pre-align with the flight line. Pilot is actually not doing the greatest job of that right now, but yeah, this was the pilot's first flight with mission guidance. Now, looking at this, I can see that the pilot is actually flying too high. So right now he's still a little bit above the flight line's height plus tolerance, but now he's making his way into the corridor. Now we can open settings and mission guidance, and we'll see that the pilot just hit the corridor, but is now actually flying below that corridor. So let me go through some options here. First, at the top, we see units for distance and velocity, and those are the units that are shown here, knots and feet. Then we see our altitude reference. Right now we're using altitude above ground, and that works because we have a height map. If we didn't, it would show an error here. We can also select altitude above ellipsoid, but that's usually not what we want. So I'll switch this back to above ground level. We can select to not show a background map, but usually pilots prefer to have some context about where they're flying right now. Also, sometimes pilots tend to get a little distracted with the map, just visually distracted. So we added an option to just desaturate the map, because really it's not really that interesting what the name of the street you're flying over is. It's more to give you some visual of whether you're above the water or where you're flying, so you can orient yourself on upcoming buildings maybe. Render quality can be changed, so this is multi-sampling and some other settings, and it really doesn't make that big of a difference. This setting is if there is no flight plan loaded, like at the beginning of this video, then how much area do you want to show? Do you want shown around the vehicle? In this case, it would be 10,000 feet. The next one is for pilots that like to show what we call the range rings. So some pilots like rings 5 and 10 nautical miles around their aircraft to give them an idea of when they will reach what part of the map. You don't see this here right now because it's they're spaced 6,000 feet. If we space them, say 60 feet, you'll see them in here. If you like, you can show not just the dynamic whiskers, so this pink line, but you can also show static whiskers, and you can configure their curvature. So right now they're set for a standard turn of 120 seconds. More importantly, or most importantly, you can configure the horizontal and vertical tolerance of this corridor. So right now we have a tolerance of 120 feet to either side, and a vertical tolerance of 50 feet, which our pilot is sometimes violating. So let me increase this to 100 feet, and you'll see that this corridor has now become much higher, and we're well within that tolerance now. Now, when you set those tolerances, the question is really, what's the point? So if you set a corridor and the pilot leaves that corridor, does nothing happen? Because all you want to do with that is set some expectations of precision, in which case you would leave this at do nothing. But if you want something to happen when the pilot does leave the corridor, you would select a different entry here. So for example, once you leave that corridor, you could reschedule the same flight line. So it would be reset to blue, incomplete, and would have to be reflown. Or you can have it reset to incomplete and schedule the next incomplete lane. In this case, that would be flight line 3. I'll leave this right here, but yeah, this is configurable. Right now, the view is oriented so that the vehicle always faces up, and you can change this. For example, here to bearing, because we can see that the flight line itself isn't really oriented straight up, and that's because we have some crosswind, so we have some crabbing going on. So the vehicle's orientation doesn't quite match the vehicle's direction of motion. And if I change this, then we now orient the view according to the vehicle's direction of motion, and you'll see that the heading is actually a little bit off. The vehicle doesn't really look upwards, but slightly tilted to the left. Most of the time that's a really small difference, but some pilots have a really strong opinion on that. You can also switch it to always be oriented north, but usually I would recommend you leave this at heading. These 1,000 feet are the look ahead distance for the vertical view, so that's this box down here, and right now we are looking 1,000 feet into the future. So we can of course change this, for example, to 5,000 feet, and then we'll see the end of the flight line coming up a little sooner. If you're not seeing the end of the flight line in here, you can still see it there. Now, the last part, or the last option here of mission guidance is what we call touch and go, and that's actually slightly more advanced, with the idea being that the operator doesn't always have to schedule and say dictate lines. We can just have the pilot do that. So we know the pilot is going to approach this flight line because this is a flight of the past, of course. But I could technically, just as an example here, I could have flight line 4 next and have it auto scheduled. Yet with touch and go mode enabled, the pilot just has to touch the beginning or end of a flight line within tolerance to start it off. So even though this flight line is scheduled, the pilot is free to still start this flight line just by flying into it. So now the pilot flew into the beginning zone of that flight line, and it automatically activated only because this option was active. If I remove this now, of course, we're not going to deactivate the flight line. So that's pretty much mission guidance. I do want to make a small jump to AGL Oracle, and that's the section down here. So we had a couple customers that said, well, horizontal mission guides is great and all, but really we're flying a corridor, a power line, a pipeline, and really we can see what we're flying over. So we don't need horizontal guidance, and we don't want to create a flight plan. But what we do need is to keep our height above ground, because maybe it's something scan range related. Maybe we don't want an MTA zone border to be on the geometry that we're supposed to scan. So really we're just interested in height. So that's what we created AGL Oracle for, and I will quickly move this over here. So this can also go to the pilot display, and it's really completely independent of mission guidance. So you can close mission guidance and not use it, or you can, totally up to you. So this window shows essentially just your altitude. Let's set this up and say we want to fly 3,300 feet AGL, and we want to have a look ahead of 5,000 feet. What that means is Spatial Explorer is now going to use its height model. So again, it needs a height map, and draws a line at 3,300 feet AGL, and it shows you where you are right now at 3,277. So you need to be flying 22 feet higher than what you're currently flying. So it's kind of comparable to the vertical view here, but this one, of course, is attached to a flight line, whereas this doesn't need a flight line and just works relative to ground. In fact, if you just scale it right, you may even be able to see ground down here. And as the vehicle turns, of course, you'll see the ground model change. So this is a real-time prediction of how ground is going to flow right ahead of you. All right, so let's go back to the slides. Conrad, could you share them? Thank you. Okay, so that's the how. And we've had Troy Ballard of Phantom Aerial Solutions test this and beta test it and give us some feedback. And he kindly, thank you, Troy, I think you're listening here as well, allowed us to share some results. So on the left side is a previous trajectory flown with ForeFlight, and you can see it's working, but you can also see it's not quite as accurate because you're using the GNSS receiver in the tablet, I believe. It's not quite as high frequency, and it's really not made for aerial acquisition. Yeah, depending on how conservatively you lay out your flight plan, that may still work, but you're going to be less efficient because you're going to have to plan for more deviation and for more overlap and so on. And on the right side is the first flight that resulted from the first test of mission guidance. And in all honesty, if you look really closely, there still is, like on the right side, there's 2 flight lines that were reflown because of tolerance settings and whatnot. But you can clearly see a big difference in accuracy and line following. And that's, yeah, exactly what we were hoping to achieve, because once you gain confidence in flying that way, you can much better, like you can plan your missions with less of a buffer, and then actually save a lot of time. And time in helicopters is expensive. So yeah, looking at this, I'm quite happy with those results. Conrad, can you go to the next slide? So here's an example, because really the resulting flight pattern is one thing, but what we're after is A, efficiency, and B, of course, also accuracy. And this is an example of a manned aerial acquisition with the Ranger LR Lite. And there's really 2 metrics of accuracy here. On the left side is that's a crop from the LiDAR Snap 4 report that uses strip-to-strip alignment by finding correspondences between flight lines. So you want to have that overlap between flight lines for trajectory optimization to work well, and that's where mission guidance also helps. And yeah, in this example, you can see the flight line or strip-to-strip distances, or the histogram of correspondence residuals. So you can see them matching quite well. And yeah, according to Troy, the worst separation from, so in terms of absolute accuracy, the worst separation to 200 checkpoints was less than 2.5 centimeters. So that's an example of mission guidance helping both in the field as well as in post-processing. Yeah, so summing up the benefits, you have the peace of mind that you won't have any gaps, you won't have to refly, and it's always easy to plan flights, but once you're sitting in say an R44 with 3 people and you're crowded in the back and everything's the sun is shining on your displays, and you really need something intuitive, something that works, and something that guides the pilot. So pointing your finger at some house at the horizon saying go there, that just never works. So yeah, we're quite happy to see this working. As part of or as far as initial feedback, we're hearing that pilots pick it up quite quickly because very visual and very intuitive. Yeah, pilots they tend to develop this I guess this code of honor to really stay close to the flight line, and you can see quite the difference, and it becomes a bit of a sport for them to yeah, really do well on those flight lines. And usually you start with a trajectory, sorry, with a corridor tolerance of, I don't know, 50, 100 feet, and you realize it's you don't even need that much. Even on windy days, you get more crabbing, which can be an issue as well, but usually they stick to the flight lines quite well. Yeah, as I said, when you have proper overlap, then that helps the LiDAR SNAP4 algorithm to find correspondences between flight lines, and that helps accuracy as well as for author generation, because sometimes when you sometimes it's not the LiDAR that is the constraint for flight line spacing, but it's the camera, right? And then you really want to be spot on so you don't have any gaps in your ortho. And in the end, when you fly a good flight plan and it's obvious to the post-processing department of which flight lines should be used and which are maybe more freestyle to ferry from A to B, then there is less communication and less misunderstanding of, I didn't know I was supposed to use that flight line as well, and can you please add that and redo this, and okay, but now I need to re-optimize, and the ground control report, and so on. So it's much simpler when it's obvious to the post-processors what needs to be fused. And it's just, there's less communication necessary. And post-processing, I mean, flying a helicopter is expensive, but post-processing is as well. And any kind of gain in efficiency is really helpful. And on the right, I don't know, Conrad, if you can click that video, that's just a short impression of one of our test flights. So that was in in the helicopter. I think this was in R44. You can see him just finishing a flight line and just jumped over immediately to the neighboring. I think this was a bore sighting flight. Yeah. Conrad, if you can go to the next slide, please. Thank you. Yeah, so this is the last slide. If you would like to know more about mission guidance, if you would like to test it, if you have ideas, we've heard some pretty cool ideas for what else people would like to do with this. And yeah, this is not done. It's working now. It's working reliably, and we would love for people to try it and yeah, give us some feedback. So yeah, please contact your sales manager and let us know if you're interested. Thank you. I believe, yeah, Lido, I think we got a couple of questions. Maybe we can go through those.
Yes, we do. And yeah, obviously we're very excited about our new mission guidance product, and we think it'll bring some bring the value of a Phoenix LiDAR system to a whole other level for the manned heli systems. Anyway, we do have a couple of questions here. The first one, well, was asking if the flight plan was for our Ranger XL or VUX 240 system. No, I can't. I have to say that that flight plan that we did in the demo was not. I can't really say what it was, but the results are similar with any of our heli-capable LiDAR systems, whether it's the Ranger LR or the Ranger XL or the Ranger Ultra.
Yeah, in fact, so this was just a nice flight plan because it has bore sighting as well as mapping, and we do a lot of bore sighting, but we don't do a lot of mapping because we don't do services. So so that's my best example flight plan. That's why I use that. But in the end, of course, we don't really care what system you fly on those flight lines. At least the software doesn't. You would probably need to find a very bold pilot to fly a Scout 16 at 50 meters above ground, but the software doesn't really care. And in fact, we call it mission guidance because you might as well use it in a car, and you absolutely can. So just reflow those flight lines a couple feet above ground and you're good to go.
Okay, the next question we have is, I think I know the answer to this one. The question was, how is the current AGL altitude being calculated? Is it being done by the LiDAR sensor or by the GPS altitude? And I'm pretty sure the answer is that it's done by the GPS, mainly because that's the more accessible value. If we were to do it from the LiDAR system, it would take a lot more calculation. It would take a little bit more time. The GPS value is readily accessible for us to display and calculate and display on the monitor system.
Yeah. Yes, if I may interject, Lido. There's two ways of doing it. One is against a terrain model, and that could be like I showed SRTM or really any model. And the other one is LiDAR. The problem with LiDAR is that once you get into the MTA zone problems, so during real-time acquisition, you may not know in which MTA zone a point lies. So if you shoot slowly, and there is no MTA ambiguity, then yes. But if you shoot more quickly, then it's really not a reliable measure. And even if it was, you could still have high trees adding noise to your result. And sure, we could filter this out, but it quickly becomes quite complicated. And there's some ideas on what to do with that. On the other hand, what we've heard so far, the height maps and the geotiffs for height work really well. What's slightly annoying, of course, is that you have to download it. And a common question is, well, if Spatial Explorer already has a height model, as you can see in that terrain layer, then why do I need to download additional height maps? And that's a valid question. But SRTM, I think, was acquired in 2000 or something, or it's even older. And some parts of the world have changed. So especially for those customers that fly over open pit mines, we got some feedback saying, well, it's great, but really terrain looks different here now. And then, of course, the idea is, well, why don't we fly it once? And then essentially half of what we do is build terrain models, right? So now you can create a geotiff from your last scan and reuse it for mission guidance in the next scan. And that's what that usage of geotiffs allows you to do.
All right, the next question we have is a very good one. Can this system be set up prior to flight such that an operator would not be required?
I think so. We haven't tried yet because it's easy to say, yeah, sure. And yes, mission guidance will pick the next flight line. But I think the devil is in the details. So I don't think I've ever had it in one of our test flights that we flew exactly what we planned. So there's air traffic control, there is cloud cover, there is fuel concerns. There are so many things that can cause you to say, oh, okay, I'd rather fly here or there. And yes, there is the touch and go mode, but we really haven't tested it with just one pilot. And so far what I heard, it's really not, I guess, proper. You should have an operator that takes care of the system, and the pilot should not be concerned with the mapping part of it. And I don't quite see how that would be realistically possible. Like, you do want to monitor the sensors, you do want to monitor GPS. Yeah, I don't know. Like, if it works, great, but I'm not sure that's a great idea.
Okay, the next question. Will it show optimal flight strip where the drift of the IMU will not influence the accuracy?
Sorry, will it show what?
Will it show the optimal flight strip or flight line where the IMU drift will not influence the accuracy of the scan?
Oh, no, it will not, because any straight line is going to make an IMU unhappy at some point of time. So the more money you spend on an IMU, the longer straight lines you can fly with less drift in mostly heading. But it's really, yeah, any IMU will suffer over time. And we have some graphs of what IMU is going to drift how much over what length of the flight line. And sure, fiber optic expensive IMUs do better than MEMS IMUs, but they all have that same problem. So it's really more what kind of drift are you willing to accept, and how much do you trust trajectory optimization to correct that drift over time, and that depends on your terrain. So it's really, it comes down to experience, and no mission guidance does not like warn you, you've been flying straight for 5 minutes, please make a turn or something. So that would have to be part of flight planning then.
Okay, we do have another interesting question here. Do we have plans in making the scan rate a function of velocity in real time? They often deal with strong headwinds and tailwinds, and having the scan rate respond to the velocity could be advantageous. Is this something that's even possible?
No. So in the case of Regal scanners, you cannot change the measurement program as you fly. So that's a no. And when you switch off and switch back on, then you have a, say, a 5 or 10 second gap in there. So no, you cannot.
Okay, that sounds pretty definitive. And one other question we have here, will the software be available for non-Phoenix systems?
No. If there is demand, we could, so I guess the beauty is that this is tightly integrated with Spatial Explorer and the system. So you don't need to have, like on the operator laptop, you don't need to have 5 open windows and use your trackpad to switch between windows and all that. The downside, of course, is that it's integrated with Phoenix LiDAR systems. If there is a lot of demand, then that's something we can consider, but for now, no.
Okay, that is it for all of the questions we have here. So I think we should probably wrap it up. We're heading towards almost an hour. Conrad, Ben, any other closing comments you'd like to give?
No, just once again, thank everyone for joining today. And
Yeah.
thanks, Ben.
Yeah, thank you guys for bearing with us. It's been fun, and yeah, be happy if you tried it out and had some good or bad feedback, so we can improve this. Thank you very much, everybody.
All right, this has been the September 2021 Phoenix LiDAR Systems webinar. If you want to see a replay of it, you can go to phoenixlidar.com and go to the news section to request a replay link. And thank you very much, and we will see you next month.